Hello everybody, how you doing? Welcome to another flipped lecture for chemistry. Are you ready to go? I am. Let's jump right into it. We're talking today about the Octet Rule. The Octet Rule is the fundamental underlying philosophy that helps us understand bonding. So today we're all about bond. Oh no, wrong bond. Sorry, not that one. No, we're talking about chemical bonds. Sorry, go away. Bang. Okay. Atoms tend toward the lowest possible energy state. By that we mean the way that their electrons are configured. They want to have the lowest possible energy available. Lower energy means more stable. Think of it as napping, right? When you're not napping, you've got high energy and you're like, woohoo, here I am. I'm not napping right now, right? But then when you're napping, Now, if somebody comes up to you when you're awake and they poke you, you're going to poke them back. Somebody comes up to you while you're sleeping and pokes you, you're sleeping. So you're more stable. Low energy, more stable, right? Solitary atoms that are not in a bond they have partial valence shells. And partial valence shells are not as stable as a full valence shell. And so they want to have a full valence shell. Now I'm going to say want many times. Atoms do not have a mind. They don't want anything, but they behave as if they do, right? So we're just anthropomorphizing the atoms. Is that the right word? And so they are going to behave as if they want a full energy shell. So if they can ditch a few atoms out of their empty energy shell and show you a full one, they're going to be happy. Or if they're almost full and they can just grab a couple more to be full, then they'll be happy. So they're going to tend toward the most stable configuration, which is a full energy shell. Okay, so when they bond, they are achieving this more stable form. So you'll see energy profiles later on in chemistry. For right now, these are atoms all by themselves, floating out there lonely and sad. These are atoms that are bonded and in a chemical bond. And you will see that their energy is lower. They're more stable. And so through the reaction, and don't worry about what all of these things mean, but through the chemical reaction, right, they go from higher energy to lower energy, and they're more stable, and they're happier. Aren't you happy when you're napping? I'm happy when I'm napping. Okay. The Octet Rule says that main group elements, things that have an S or P valence electron orbital, they are more stable when they have 8 electrons in their valence shell. And you can see that because main series elements, they have an S, that's 2, and then they have a P, that's 6, and so 2 and 6 is 8. So if they have 2 in their S and 6 in their P, then they're full. Their valence electron shell is full, and they want to be full. They want to have 8 electrons. So that's called the Octet Rule. Octet means 8, or oct means 8, okay? So if this guy only has 3 electrons, I feel so lonely. It's like I'm incomplete. Oh, it's okay, nitrogen. It's all right. We'll make friends with you. It'll be okay. No, not nitrogen. Lithium. There we go, making a mistake. Okay. But if you look at the Lewis dot structures for atoms in the main series here, these guys all have 1. These guys all have 2. These guys all have 3, etc. When we get up to the noble gases, they're full. They have 8. So these guys could ditch 1. These guys could ditch 3. These guys could pick up 1. These guys could pick up 2. So we already talked about how the columns help you see the charges. They also help you see which way it's going to go as far as gaining or losing, right? Because the ones in the middle have to either pick up 4 or lose 4. They're going to probably do a different kind of bond. The ones that can only pick up or lose 1 or 2 will be the ones that want to go this way. Okay? They all want to have 8, though. That's what it's all about. They all want to have 8. So the Octet Rule, somebody else's wording of the Octet Rule, atoms tend to gain, lose, or share 1 or more of their valence electrons to achieve a filled outer electron shell. Maybe that's a better wording for you. Here's another one. In chemical compounds, atoms tend to have the configuration of a noble gas. That's another way of saying it, right? They tend to try to get full, and noble gases are full. So, 2 main ways that you can get this done. One is ionic bonding, where they give or take electrons. In an atom with with an ionic bond has given electrons away or taken electrons from something else, and then that affects its charge. It now becomes an ion. If it has gained electrons, it's negatively charged. If it has gotten rid of electrons, then it's positively charged. And so the charges now, these ions, will attract each other. Opposites attract. So sodium chloride, table salt. Sodium gets rid of an electron, and now it's positive. Chlorine accepts an additional electron, and now it's negative. And then the positive and the negative attract each other, and we have table salt. So that's how an ionic bond works. We've covered this already before in physical science, but this is just for the sake of review. Okay, here's some pictures. Here is sodium and chloride. Sodium and chloride want to form a bond. So sodium gets rid of an electron and chlorine picks it up. And now sodium is positively charged and chlorine is negatively charged, and they're attracted to each other, right? It takes a little bit of ionization energy to get rid of that electron out of sodium, but you actually get more energy back when the chlorine receives that electron. So it's net positive energy output. And this is an example of an ionic bond. Here's another example. Of course, dogs are fun. We like dogs. So here's sodium dog and chlorine dog, and they both have a bone. But sodium dog would like to give its bone to chlorine dog. And now chlorine dog and sodium dog are attracted to each other because they're opposite ions. Doesn't that help you? Everything's better with dogs, right? Okay. Covalent bonding is the other way to get this done. Not give and take, but share. They share electrons. These are electrons that have been to preschool, right? Two atoms satisfy the octet rule by sharing enough electrons so that they both feel like they have a full valence shell. No additional electrons are involved here. They just both agree to look at them together. And so they said, this is mine and yours, and now we get to share it. So here's an example of two elements that have 5 electrons in their valence shell. So two atoms that have, 5 in the P, but they would have 7. There you go. And so they both want one more. They both want one more. And if they can look at each other's lone electron, then they share that pair of electrons, and now they both feel full. And so because they both feel full, they're happy. And they're bonded because they're sharing those 2 electrons. It's like they're both hanging on to the same bones. We'll get to the dogs in a minute. Here's oxygen and hydrogen. Oxygen wants 2 more electrons. Hydrogen wants 1 more electron because he's full at 1s2, right? So if they share, then they all feel full and everybody's happy. And hydrogen is sharing these 2 electrons with oxygen, and this hydrogen is sharing these 2 electrons with oxygen. And the electrons around oxygen look full, and the electrons around hydrogen look full, and everybody's happy. Aren't you happy? It's as if they're sharing, because they are. Here's just some other examples. This is phosphorus trichloride. Phosphorus sharing an electron pair with each of 3 chlorines. Water is an oxygen sharing an electron pair with each of 2 hydrogens. Carbon dioxide is a carbon sharing 2 pairs of electrons with each of 2 oxygens. Okay, here's our dogs, because dogs make everything better. So one dog has a bone and another dog has a bone. And when they get together, they decide to share both of their bones, and now they're bonded. Okay, there you go. That's a chemical bond in dog terms. Octet rules. We can make single covalent bonds, we can make double covalent bonds, or we can even make triple covalent bonds, depending on how many electrons these things want to share. So sometimes it's only 1 and we call that a single bond. Sometimes it's 2, we call it a double bond. Sometimes it's 3 electrons each, and that would be a triple bond. The more pairs of electrons that are shared, the more stable the bond is. And so single bonds, fairly easy to break. Triple bonds, you got to get a crowbar, right? And so the more stable these bonds are, the lower energy and the happier these 2 atoms are with each other. This is just a picture of a double bond, more stable than the single bond. 2 oxygens sharing 2 pairs of electrons, right? Here's what it would look like in a diagram of energy shells or of orbitals. These 2 carbons are sharing a pair of electrons end to end, like this. And then the p orbitals, this is the s orbitals, the p orbitals that go up and down from these carbons overlap. And so they get to share these electrons here, and that's called a pi bond or a double bond. You can also have the double bonds written multiple ways. This is an example with another model. Here's a sigma bond, 2 s's that are shared. Here's the pi bond, 2 p orbitals that are shared. This is a double bond, right? It's got a single and the pi bond. So this is what a double bond looks like. Triple bonds, same idea. They share the sigma, they share 1 pi, and then they share another pi. And so they wind up looking like this. This is a triple bond. Alrighty. Metals. Metals, comrade. Metals are communists. And the reason I call them communists is because they all, this pile of neutrons, pile of nuclei, there you go, of all of these metallic atoms, they share their electrons loosely throughout the whole piece of metal, which is why metal conducts electricity so well. It's because no one nucleus is hanging on to the electrons exclusively. They just share them out. All their valence electrons get shared out. And so because of that, they conduct heat, they conduct electricity, and they're very easy to get to hang out together because they don't really care if they individually have 8 electrons. They just say, hey, you got some, I got some, let's hang out together and we'll have enough and it'll all be great. So these share communally all the electrons in the piece of metal, all right? So metallic bonds are just shared metal bonds. Here's an image to help you see that. We have a bunch of positive nuclei and a bunch of electrons zipping around amongst them, and that is what a piece of metal would look like at the atomic level, okay? And again, just another picture of that, a whole bunch of positive nuclei and a bunch of electrons just running around in there. A sea of delocalized electrons in a giant metallic structure. Metal cations and floating free electrons. Okay? And again, dogs, communist dogs. They each come to the picture with their bone, but they don't have enough bones. But if we all share our bones, maybe we'll feel like we have enough bones, right? And so this is the example here. I hope my dogs and I have helped you understand this. If you have any questions, please post them in the comment field below, and I will get to them as soon as I can, or I'll see you in class tomorrow. Alrighty? Jesus loves you, and so do I. Have a great night.